Okay.
I don't know. It did this last time where I had it muted because now it's picking up.
Yep. Cool.
Okay. I'll keep you updated if it runs.
Share screen. All right. Are we? I would like to be able to. All right. I think we're back. Now it's software time, with audio this time. All right, so we're putting our DFMAs up here first, unlike other teams, because we're different like that. A lot of our issues come down to we didn't find a bug in the code, and that bug causes stuff to break. That is, in fact, what a lot of these are. Our main mitigation strategy is just test everything repeatedly, always and all the time. And if it's never come up in testing, it's probably won't come up in competition. It's not a perfect solution. There's not really a better one for software. A lot of other ones include that if the robot goes and drives into an obstacle, it could go and break stuff. Hopefully, drivetrain's new improved systems will make that so that even if we do drive into an obstacle, it will cause less damage. And also, we have driven to obstacles historically, and it hasn't caused many issues. So, shouldn't be an issue. And then a lot of other stuff is just if we fail to go and see a crater, we drive through a crater. Although, once again, we've done it before. It'll probably be fine. Really sorry if we drive through craters, drivetrain.
All right. So the first thing I have up for presentation is basically the autonomy version of the concept of operations. This first one is going to be the overall behavior cycle. So this is sort of what defines what we are going to do when we're autonomous. So the first thing is that we go to traversal mode, in this case, raising linear actuators. We're going to spin 360 to generate like a sort of starting map of our where we are, right? If we're not able to see April tags in that initial sort of 360, which I expect we will be able to, but if we're not, we can do it one more time. And after that, we will plan and traverse to the mining zone from the starting zone. This is sort of labeled as traversal autonomy, right? Once we complete this, we will get the traversal points. And once we've arrived there, it will basically be an excavating, planning to the berm area, traversing there, aligning and depositing, and then going back to the mining area, sort of up and down as we stay autonomous. And this section is the excavation and dump autonomy, of course. And the whole thing together, if it can be completed without manual intervention, is the idea of full cycle autonomy. The next sort of plan I have up here is sort of the strategy for basically what we are going to do during the competition, right? So the first thing is initialization in the top left. After that, we're going to try traversal autonomy, right? If we are able to successfully traverse to the mining zone without manual intervention, we will move into excavation and dump full run autonomy. If we are not, then we will take over basically, manually traverse the excavation zone and keep doing the same thing. So once we've arrived at the excavation zone, we will start our excavation and dump full run autonomy. This involves making 3 or more trips from excavation zone to the berm zone, mining and depositing, obviously. And if there's a minor issue during this, such as something we can easily recover from, we can manually adjust the position of the robot, sort of give it like another start and try again for a full run. However, if there are repeated issues or some failure that we're not able to easily recover from, we will also take back manual control over the robot, and from there try and do the 1 cycle excavation and dump, which is a much sort of simpler autonomy procedure, right? If we are successful in the full run excavation and dump, and there were no previous manual adjustments, we will go to full autonomy, or not really go to, but continue, because we've determined that if we are able to make it to this point without any manual control or involvement, it's worth the extra 100-point bonus we would get to just sort of continue doing it in full autonomy. On the other hand, if we did have previous manual adjustments, we obviously can't get the full autonomy points. So once we complete our full run of excavation and dump cycle, we can switch to manual control to try to earn some mining points in manual mode. That's about that for the overall strategy. And
All right, so this year we're working on improving the previous MPC controller with a new algorithm called peer pursuit. So pretty much just a high-level overview. What it's doing is it's creating a virtual circle around the robot, and it's finding the intersection between that circle and the path. And then it's navigating to that point instead of just the closest point to the path. So if an analogy to how this would work in real life is if you were to take a cart and then drag that along with a string, it's not exactly just going to the closest point, but it's got more of a smooth curved motion. And you guys can see it working in the video or GIF above. So right now it works in the simulator and it's been tested on the robot. Currently it has similar performance to the MPC, but this is with untuned values. Right, currently it's really jerky and it's not able to stabilize and do the smooth continuous moments that we see in sim. So it still needs a lot of tuning and testing to see how well it will work in the real world with the sand.
So another thing that we're working on is adding a second camera to our robot to allow it to more easily find craters and map the area over a wider area. So we've made significant progress towards that. We have rewritten a lot of our code that used to only work for one camera to make it work for two cameras. And we are back to the same spot that we were at. So we found that it's likely that we will have two cameras on the robot, and some possible mounting locations will be facing backwards so that we can see in both directions if we have to traverse backwards to more easily do our excavation and dump full cycles, or pointing downwards to more easily see craters so we can avoid them in the future.
So one thing that software has typically had an issue with is detecting craters. That's been kind of our one of our biggest issues that we've had at competition. So another thing that we're trying to implement, in addition to the multiple cameras that Ankur was talking about, is implementing a 2D LiDAR, but that's angled so that we can see a plane that's right in front of our robot and generate some kind of point cloud based on that. So you can see in the pictures above, it's kind of working. This is with the Pringles can in front of it, and you can see the resolution that it already has on it. So we're hoping that this gives us a better estimation of where the craters are and helps us update kind of our occupancy grid on where we can path to whenever we're doing our path planning and our path following during the competition.
One of the other things we need is situational awareness cameras. And these are just USB cameras that we can use for information. And the reason was, as just was mentioned at the very beginning, that we lose 60 points for every arena camera that we use. And we would rather not lose those points. However, we still need to see what we're doing and understand what we're doing, understand if excavation is stalling, how full that position is, understand if we're just understand where we are in relation to the rest of the field, so we don't accidentally go and dump while we're still in the excavation zone and not get points for that. So we, so far, have been able to run up to 6 cameras simultaneously. And that is what that image is we have 6 different camera feeds coming through. We do need to consider USB bandwidth and also communication bandwidth from the robot to the computer, and also latency. It's not very much use if all the cameras are 20 seconds out of date. We are working on that. We are working on potentially compressing the streams to save on that bandwidth. However, this is my call and request to all the mechanical teams. We will need a place to go and mount all of these cameras. And we will need to talk more about that, but that is a thing that needs to exist. These cameras do need to be mounted somewhere.
We also got the load cells of the robot working. They're basically act as little scales underneath the deposition system that essentially track how much mass is being stored in terms of regolith. This example is with a approximately 2.4 kilogram weight. It's hard to see on the screen here, but it's accurately getting tracked as around 2,000 to 3,000 grams by the load cell system.
With these new load cells, now the excavation and the deposition cycles are now dependent on weight instead of time. This is obviously a much more foolproof method of excavating and depositing. There still is a time dependency just for redundancy, just in case the sensors fail or for some reason we don't reach one of the thresholds. but this should be a much better system. And we still do need to test it and find which thresholds work best. But yeah, that's what we've been working on.
Okay, ultra widebands. We are no longer doing ultra widebands because they produce pretty low quality data. If you see that image, that is a sphere. The way that they work is they give you the distance from the base station to the robot, and to figure out where the robot is, we generate 3 spheres around each of the base stations, and the intersection points tell you where the robot is. And you can see the intersection point is about 2.5 meters off the ground, or 2.5 meters below the ground, which is in either way not correct. And they also have a very slow response time, about 4 seconds. So we do not think that they would be worthwhile to continue with.
All right, it's finally time to talk about the new motors from a software perspective. The key feature of the new motors is they have an integrated controller, which means we can remove a lot of existing code and sensors because now we can just measure velocity and current on the motor itself. It's important to note that this only applies to the new motors, not the linear actuators. So we will still need the current sensors there. The other cool thing with the motors is they communicate over RS-485, which is a protocol that can be daisy chained. So we only have one connection going back to the Teensy, and we run a wire sort of from each motor to the next motor, which just makes the wiring very simple. From a software perspective, we have the library to control the motors written and tested. We've run multiple motors simultaneously. That all works. So we're just working on converting the behavior code to send target speed instead of target torque like it used to. And we can really only finish that once we have the final robot and we test what speed we actually want the subsystems to run at.
All right, and for our last thing is our priorities that are moving forward. We mentioned pure pursuit. We would also like to create and test additional driving controllers. The big one for that is a point-to-point controller that will effectively drive straight until it hits a turn, then turn in place, then drive straight until it hits a turn, then turn in place. We're not sure if this will work better, but it should be relatively simple to code, and we would like to try it. We need to do further testing latency reduction on the arena cameras. Currently, the latency is about half a second, which is manageable, but it's not great. We'd like to get it lower. We need to do further integration and utilization of the new motors. There's a lot of code that is still reliant on the old motors existing, and the values we need to send to them are different. So we need to go and rewrite a fair bit of code, but that is underway and that is in progress. We'd also like to integrate multiple cameras and LiDAR into our SLAM, which is our mapping algorithm, and that tells the robot where it is in the field. And again, the main point of that is that so we can see craters better, so we can see rocks better, just so we can avoid driving into things that will either lose us points or potentially damage the robot. We also need to clean up our behavior flow and logic, modify the new autonomy rules. The autonomy rules are slightly different this year. It used to be that excavation and deposition were 2 separate runs. Now they are one. Now you have to do them right back to back without any manual intervention. And there's things like that we just need to go and adjust. It can also clean up a lot of the code. A lot of it was written at competition and is therefore not very clean. It's just in the it needs to work for the next 2 hours mode. We would like to fix that before going to competition again. And of course, just more testing. Testing everything always, all the time.
Yeah, on the final note of testing, I just wanted to point out that a lot of what we do is sort of based on how we can effectively model the robot's traversal through the weird environment, sand, right? So to mechanical teams, the sooner we can test using both new motors and the sort of structure of the drivetrain and the new wheels, the better, right? One thing that we struggled with last year is not a whole lot of testing time at the end of the year with the new robot. So yeah, obviously take your time, get it manufactured right, but the more testing time, the better, obviously.
All right, and that is all from us. Any questions? Hans?
Yeah, so kind of directly on that note, we are actively in the process of making those practice wheels, and those should be done before Tuesday's meeting. Will you be able to test with those, or do you think that the results you get from that will be inaccurate using that stream?
There are a lot of things we can test with it, and a few things we can't. So new path following, right? It's not going to be perfect under the old robot system, right? Because just the way it'll respond to wheel commands will be different. But we can test a whole lot of other stuff that we still need to test just driving around in the pits, right? Driving around in with the practice wheels on a flat floor, so we can test slam, so we can test like able tag range. There are still a lot of uses for it.
Peter.
On that note, you said that Pure Pursuit needs more tuning for it to produce more continuous smooth motions. What does that tuning look like, and how similar is that tuning to tuning that would be involved in getting MPC working?
Yeah, so I can't exactly.
You can come to the camera.
I can't exactly speak for the MPC tuning process, but specifically for the tuning process for Pure Pursuit, we've implemented a slip controlling PID loop. So the angular velocity of the robot is controlled by whatever the SLAM is recording, so what the actual velocity of the robot is, and how much the heading difference is from the target point. And then for the linear velocity, we're just using a PID loop. So that's 5 values that need to be tuned based on the response of the robot and the way the sand behaves and the outputs of the motor. So those require testing, just running it on the sand pits and slowly modifying those values until the robot's responding the way we want it to.
An important note in relation to MPC is that MPC has already been tuned. MPC has been extensively tuned over at least the past year. MPC has already been written and working and just needs tuning. The reason why we're so excited about Pure Pursuit is that in its untuned, just let's go and throw a random guess at the value. It already behaves about as well as MPC does after a year of effort. So if we put a year of effort to Pure Pursuit, it should work even better. Julian.
So obviously, I know we're hoping for autonomous excavation.
Of course.
Position. I know last year we often had to do manual mining.
Yes.
And one issue with that I think was driving the robot forward.
Yes.
It was pretty difficult to control that, and it was sort of not very smooth. Is that like maybe a feature we could add this year?
Yes, hopefully. One of the issues that we ran into is that the excavation liked to stall a lot last year, and it stalled a lot even when just plunging down into the regolith, not driving forward at all. So in general, it was considered too risky for us to drive forward autonomously. So we just did do it last year. However, hopefully there will be less stalls this year. So we should be able to drive forward. Yes. Peter.
Related question, have motor dead zones been examined at all? Is there anything of note there? Would that cause any problems in terms of trying to move forward at a slow enough speed to not stall excavation?
We have not examined those. That is the thing we need to do. It'll be hard to examine that until the new motors are on new wheels. But at least in terms of the amount of precision we're giving to the motor, the last year's motors took a value from 0 to plus minus 127. This year's motors take a value from 0 to plus minus 5,000. So we have a lot more granularity in how exactly we're going to be controlling them. So we should be able to, at the very least, have more granularity in how fast we're going on the slow end.
Yeah, but if you told the motor to rotate at 5 RPM,
yes,
would it work?
In our testing, it has. Testing has not been under load.
Yeah.
And we can't really test under load unless we do some really sketchy things until we have a robot put together.
Okay, great.
Hans.
How fast do you think we want to go?
Well, we went and did a rough calculation of maximum robot speed, and if we took the motors and we spun them at maximum speed with I think 14-inch diameter wheels, a robot's maximum speed would be somewhere in the range of 76 inches per second, which is too fast. So not that fast. I think we'd be looking somewhere in the range of last year's, which was about half a meter per second, or about 18 inches a second.
I'll add in real quick just for autonomy, right? In order to be able to have SLAM map in front of us, be able to process that within time, we don't want to go too fast. So in the range of 0.3 meters to 0.5 meters is also what I'm reading.
For the 2D LiDAR,
yes.
Do you have a distance that you think is useful enough where you can see something and have time to avoid it, but not too far that you don't have values, or are you still trying to pick that distance?
We're still trying to pick that distance. A lot of it so far was just saying, can we get it to integrate into our mapping protocol at all?
Yeah.
And I think over the next couple of weeks is going to be a lot more work into what is the optimal angle for this.
would it be helpful to just have the 2D LiDAR servo like we used to, so that it is scanning kind of up and down as you're driving? Or do you think that's
We have not looked into that. That is a thing that we can look into and see if that is going to be useful at all. We will still have a depth camera for a lot of our stuff.
Yeah.
So the main thing is that the depth camera struggles to see into craters.
Yeah.
This LiDAR is mainly our just, can we see depth? Can we see the dips of a crater? And that is the only thing we need it to. So not sure if it will be completely necessary to have that servo, but you can look into it.
Yeah, adding on really quick, the depth camera, we're hoping to have it angled downwards as opposed, it's usually at a flat angle. So we're hoping to be able to see further into craters with that also.
And is the LiDAR, is it dust proof and everything, or is it?
Not yet, I don't think.
We will need to look into that.
Okay.
Yes, that is not a thing. That is not a thing that we have looked into extensively, although we will need to.
Okay.
So it seems like your load cells have been working so far.
Yes.
What is the performance gain of using a load cell versus your timing?
When we're doing autonomy, it is the amount of dirt that we take off per second is very much not consistent. Especially if we hit say a rock, and need to slow down so we don't go and stall things out or break things. We will be mining less material, and our estimated values are really just this will get us close enough. Like if we go for 30 seconds, they will say that gets us like 75 to 80% full. Maybe not all the way, but it's close enough that we're comfortable. And if we have a really, really good mining session, we don't overfill the bucket. With the load cells, we would be able to say, okay, mine until you are full. And then if we're going really fast, then we'll just stop early. If we're going really slow, then we can just keep mining for a little bit longer.
Gotcha. One more thing, you said so previous years with excavation, if it stalls, then that's why you hesitated with driving forward.
Yes.
Have you explored dynamically using the actuators to back out if it stalls and maybe dragging up over depth?
Potentially, the issue with using actuators, the actuators are very, very slow. I think it takes something like 2 to 3 seconds to completely back them out of the fully down position into where they are above the ground. So
I think what he's saying is, can you dynamically adjust the trench depth as you're driving forward to correct for stall?
We can try. We have not done that specifically. The main issue is that our adjustments are going to have to be very, very slow because of how slow the actuators are. Main thing we've been adjusting is how fast we drive forwards.
Also,
yeah,
I have a dumb question about the brushless motors.
Sure.
Does swapping our motor technology, does that give us like a minimum speed that we have to go?
It shouldn't.
Okay. So you think that these will be able to go anywhere from 0.1 inches per second to your crazy number?
In theory. One of the things that these also have a very, very odd torque curve. And in theory, they have the exact same torque from 0 up to 3,000 RPM. Yes, very weird. But in theory, that should mean that we would have the same torque and we should be able to have the same power. Like we should be able to have the same driving power, whether the motor's working at 5 RPM or 3,000.
Okay. So you have the motors in hand. Have you tested it for slow?
We have tested the motors can go slow, but we have not tested that under load because we can't load the motors without putting them into something we don't have something to put them into yet.
Well, you can, just like the weight and strength.
Yeah, we'll figure it out. Hans.
So with those load cells, are you planning on using it this year's robot?
If deposition can find a way to integrate them, then we are planning on using them. If deposition cannot, then.
If they can, are you prepared to find a way to filter it? Because as this regular comes in, it's going to be dropping from this high height. You get a lot of spikes as you continuously mine it. You're going to find a way to filter it so that you can get.
The easiest way is just to do a rolling average of like the past second or so of data, and then we can just ignore every day, and just take that average and continue.
Yeah, my concern would be because it's kind of coming in continuously, you'd be having a continuously high spike, and as soon as you stop, it would settle out.
Yeah, and a lot of that is just if we go and we say that, hey, when we're mining, whenever we see a value of 10 kilograms of regolith, even if we know that settles down to only 8 when it's done mining, or something like that, then we know that then we can still just say, okay, we want 8, well, we'll just go until we see 10, and then we're done.
Just like a ballpark, how much time would you like testing on the robot? And when you say that, do you just mean like full construction robot, like it's fully built, how much time would you want with that robot before the competition, like schedule?
This is a hard question to answer because the correct answer is as much as humanly possible. And we would like the robot to be as completed as soon as possible. And if there's parts of the robot that are completed, but there's parts that are still on hold, like if say that like deposition ran into an unexpected issue, and we would still like to test on the parts that are on drivetrain because that's still important. We still need to do that.
Are you thinking like March or April, like March?
If you get the completed robot to us in March, we will be very, very happy.
So last year we had like 1 or 2 Saturdays, I believe, before we went to Florida. And I think that wasn't enough, personally. Ideally, at least a few more days where we can get down there for multiple hours, get some stuff in. It would be good, at least a few more days.
Peter.
So for SLAM, in your ideal world, are you using both depth cameras and the LiDAR, or would you use only a combination?
If SLAM can take both depth cameras and a LiDAR and still produce accurate results, then yes, we would like to use all 3.
6 cameras and a LiDAR seems like a lot.
Yes, it does.
Do we need all that? And if so, where will those cameras be pointing?
So yes, it is a lot. The reason for that many is because not all of them will be doing SLAM. A lot of them will just be for us only. We would like to have, as a rough estimate right now, we would like to have one pointed somewhere at excavation so we can see how it is performing and how it's doing. We would like to have one pointed at deposition so we can see how full deposition is. Those can be the same camera potentially, depending on how we angle it. We'd like to have at least one pointing off the sides of the robot because we would like to see like where we are in relation and have a better understanding of where the robot is.
One on either side.
Potentially. And then we'll have our main cameras probably one on the front and one on the back.
Another one I was thinking as a possibility is one pointed out the back, but not at the same angle as our SLAM camera, but maybe angled downward so we can kind of see, are we in the berm area? Are we depositing within the right zone? Because that's also important.
Yeah.
And that would be a different camera from your rear depth camera.
Yeah, the rear depth camera, we most likely want to have flat just for range of mapping, basically.
And this one will be pointed downward so we can actually see like when we start depositing, are we actually putting the dirt where we want it to, where we will get scored, or are we just putting it, somewhere? Yes.
For that, is there any way to plan for any problems that could occur during competition, where you would take less data because we can't get that transmission? Could there be any issues?
Yes. So we actually had a lot of experience with this. At last year's competition, we had a lot of communication issues. We are trying to mitigate that by one of the things we're doing is we're adding external antennas, which is one of the new robot requirements. So in theory, we should have a stronger signal and less latency and less dropout. All of our data is recorded locally on the robot. So at least after the fact, we can analyze the robot. There's not as much in the moment. Also, all of our autonomy scripts run on the robot itself. So that in theory, even if we lose connection completely, the robot can still keep on going and do what it needs to. But yeah, if we run into an unexpectedly high latency scenario, it will be difficult. But we will have all of the data, and in theory, if the robot is autonomous, it should be able to do everything it needs to by itself.
And if worse comes to worse, we can enable an overhead camera and not stream 6 sources of video back to the computer.
We can also,
if it doesn't end up working.
We can also turn off streams that are not relevant. Like if we, if the camera that is looking at the back of the robot to see where we're depositing is not relevant while we're mining. So we can probably like alternate between cameras if that is necessary to save bandwidth.
I just wanted, I'm glad you're thinking about it. I just, I guess the suggestion is to have that plan before competition.
Yes.
And the other question I had was, can you test, or is it hard to test on the existing robot, the excavation, deposition, monitoring, other excavating, collecting, monitoring? Is that possible?
Yes, and we already have a system that does that.
Okay.
We can test out changing parameters of that. but it will be hard to say because we don't know when the new one will stall or how it will behave when it does. Hans?
This is maybe more Phil's question, but does
Sure.
turning off or on the cameras violate your autonomy? If you just want to see it or not see it?
Yeah, so if
Or
you're,
no, depending on where in the rulebook you read it. The rulebook says in 2 different spots that you are allowed to go and touch your autonomy, to touch something. The rulebook states that at one point that you are allowed to go and touch a telemetry part of something that is only communicating telemetry that does not communicate back to the robot. In another part, it says you're not allowed to touch anything at all. That is an unclear statement. I'm leaning towards Isaac's of yes, you can't touch anything.
at least from previous experience, the moment our hands went to the computer at all is no longer autonomous, which I assume is their intention with the rule.
That is probably makes sense.
So if we were to do like a full autonomy run, you'd probably just leave all the cameras on.
And then just sit back and watch, hopefully.
Back with the suggestion about turning off the cameras, can you, based on, like, is there a way to know if packets are being dropped or latency is high and switch off, like automatically switch off unnecessary ones based on priority?
I can turn on and off cameras through code with scripting. I don't know about reading latency in real time.
We don't know. We have not looked into this. It is a thing to consider for sure. Any other questions? In that case, I believe it is time for power and hardware.
All right, hi everyone. Just before we get started, get something out of the way. I'm obviously not Haziel. He is unfortunately sick, and so I'm taking Haziel's place. But yes, we have power and hardware, and we're going to first start off with a little system overview of the entire electrical system. First, we have our battery that's going to be mounted somewhere on the frame of the robot, and is going to be going into our P&H box, which we've already seen it's going to be on top again this year. From there, it's going to be going through our battery protection circuit, and then to the power meter that NASA requires us to use. From there, we're going to be seeing that it's going to be going into a power distribution board, which is going to be either stepping up our voltage to the 48 volts that our new brushless motors want, or either stepping it down to the 5 and 3.3 volts that all the other things want. And then from there, it's going to break off. We've got the Jetson, that's going to be our main computer that software uses. We also have the Teensy, our microcontroller, that all of the sensors and motor controllers interface with. From there, the Teensy, since we are still using the linear actuators, we will be using the Sabertooth motor controllers. So because of that, we have the Sabertooth again in the P&H box. Which then will be going to the current sense board so we can tell when our linear actuators are stalling and not, and when, so then software can know when to stop them. And then from there, they'll go out of the box again to the linear actuators. Additionally, we're going to the Teensy, the motors have their own built-in motor controllers. So from the Teensy, we just go straight out of the box to the motors. Again, with the breaker, with the power going through the breaker board for those motors. So I think we're going to start off with the power distribution board.
So for power distribution, the main function would be to distribute power to from the batteries to all the components. The input would be 24 volts and output would be 5, 12, 24, and 48 volts. The base features is individual toggles for each voltage rails, which is controlled by the Teensy board, and emergency stop triggered physically and via the Teensy board. It would deliver a combined power of 1300 watts, and we would also have overcurrent protection and variable voltage output.
Yeah, so for the topology of the actual DC to DC converter, we chose to use a combination of a buck converter and a boost converter. These are chosen because they are simplest and also the most efficient out of all the topologies out there. And for the specific controller chipsets, we specifically looked at chipsets that are capable of synchronizing externally with other chipsets. So this will mean even with a large power load, we can just chain them all together and they will be very efficient and there will be very little disturbance because these are switch mode power supplies. The way they work is by switching really fast. So it's really helpful to have everything synchronized. And all these chipsets also have overcurrent protection, surge voltage protections, and inrush protections. So yeah, it should be really robust.
For the overcurrent protection, as a function of protecting the targeted load, soft start and stop. As you can see, the R6 represent the targeted load, and the overcurrent protection is mainly the Q1, the PNP junction. When the circuit works normally, the current will flow, the PNP junction will not be activated, so it will flow through the MOSFET and then through the targeted load. But when the current is higher than the maximum current of the targeted load, the PNP junction should be activated, which will lower the gate voltage of the MOSFET, and that will separate the targeted load from the rest of the circuit. And as for soft start and stop, it's mainly achieved by the capacitors. For example, C1. C1, although it's mainly for to absorb the interference from the input, but it's also in parallel with the MOSFET, which will increase the total capacitance of the MOSFET, and that will increase the time it takes to turn on and off the MOSFET. And yeah.
So yeah, for the DFMEAs, main failure points is just overcurrent and like just overdrawing the system. Now in normal operations, the robot shouldn't draw near to the maximum output of the power distribution board, but if it does, there are built-in overcurrent protections in the board itself. So unless loads fail, everything should be fine. And the same is for the overcurrent protections on the board and the relays. Yeah.
Now, going to talk about the current sense board. Again, this is going to be a lot smaller from last year's just because all the brushless motors have their own current sensors built into them. So really, this is just for the linear actuators. We are trying to use a new tunneling magnetoresistive sensor. Is more accurate and performs better than the Hall effect sensors. We know the Hall effect sensors work, so we've built our own schematic using that. It's basically the same from last year, but we also wanted to try these new sensors too. And we're going to compare it and see how these work out. And additionally, we're using the same ADC, and so it's all very much the same, or very, very similar to last year in terms of what it looks like from outside the current sense board. Here's a TFMEA. Really, the main problem here is there could be a board failure when we solder it. It is very potential. It could have some potential shorts, just some solder bridges that it just mean we wouldn't get any data. We can detect that pretty easily. That's the only really big thing that I'm worried about with these boards is when we solder them. But with that, we're going to go to the Teensy board.
Yeah, so over the past few weeks from the previous design review, we've kind of come together, made a block diagram and the schematic you see above. This year's Teensy is kind of basic. We don't have a lot of sensors and encoders to include since the motors have built-in encoders and stuff. So the main chip components we're using are the MAX3485
chips that will translate the RS-485 motor protocol to the UART. So we have 2 of those for the 2 signals. And we also are reusing the BSS 138 to step down from 5 to 3.3 volts, especially in cases for the LED strips, because those are run off of 5 volts. And we're using the LED strips just for software, just to be able to tell if what mode the robot is in, if it's manual, automatic, and other status indications as such. Yeah, and kind of to go over the DFMEA for the teensy. Like with the current sense board, there's just trouble if there's loose connections or poor soldering. So honestly, we'd be pretty much able to tell if there's something wrong. Obviously, if we can't, if there's something wrong with the MAX 3485 chips, we won't be able to communicate with the motors. And yeah, so that's pretty much it. So now we'll move on to box design.
Okay, so for the box design, we're kind of taking a look at the CAD from last year, but as you can see, our needs this year are a little bit different as we have several cameras to use. So we're gonna have 7 USB ports, which in this CAD is kind of temporary, but you can kind of see them right there. And also have an RSJ45 like Ethernet port to connect to. And we're also gonna use Anderson power poles for like motor stuff, and also like a 15-pin connector for the sensors. None of that is represented there yet. It's very temporary, tentative, and subject to change, but we have all the stuff we need for that. We just need to kind of like put it together in the CAD. And yeah, of course, we'll have PCB mounting holes for all the boards on the inside. And we're gonna kind of adjust like to match the schematic you saw earlier and like align everything. And yeah, like all the bulkheads, that's proof. Yeah, this is what I was talking about before with the motor bulkheads, and yeah, I pretty much cover everything there. But also we're gonna have the e-stop button, of course, the insertion for that, and antenna mount, which is I heard is a new thing this year. So yeah, all of that you see will be integrated into that.
And these are just the DFMEAs for the box design. So the biggest or most severe point of failure would be dust getting inside of the box. Obviously, that's why we're dedicating a lot of resources to making sure everything is dust proof, running all the wires through bulkheads and whatnot. So we consider that to be pretty unlikely, hopefully, but that is kind of our largest point of failure. And with the bulkheads, any of the failures, as long as you make sure that they're rated for sufficiently high current and well dust sealed, we don't anticipate any problems with the bulkheads.
Sweet. All right, the breaker board. Again, this is gonna be fairly simple. Basically, we are going to be doing practically the same thing we did last year, where all of our motors and high power electronics will have auto reset breakers in front of them. And so that will just make sure that it's kind of the last resort to make sure that they're not drawing too much power, they're not stalled for a long period of time that would damage the motor. With that, oh, that slide didn't make it. Kind of finishes up P&H. Our priorities moving forward is I did at the very beginning mention the battery protection circuit. That is a little bit behind schedule compared to the other projects we have. But basically what we are doing with that is we are, since NASA requires us to plug our battery directly into that power meter, that is only during competition runs. And so what we are planning on doing is for non-competition runs, when we're just working on the robot, we're going to have a battery protection circuit in there with its own relay in between the power meter and the battery that will be able to cut off the battery completely from the circuit. With that, we are going to be finalizing and kind of doing our own internal schematic review to make sure that all the schematics are good. We don't have any of the problems we had last year. And also, hopefully before winter break, we're going to finish the layout for all the boards and send everything over to JLC to get those boards manufactured and shipped to us. And additionally, by CDR, we're gonna have the robot wiring diagram done. So with that, I'll open it up to questions. Yes.
Have you guys been in, did Peter talk to you about proto case? or have you guys been in contact? Those are the people that manufacture our P&H
Yes,
box
yeah.
for us. Okay, so they have like certain CAD guidelines too for, so
Yes.
you guys have been, okay.
I think maybe you'll talk with Peter a little bit about that more.
Yeah.
Yeah.
Okay, sounds good.
Yes.
You mentioned 2 max 345 chips. Can you clarify why that is?
Yeah, so just like looking at the data sheet, there's a positive and there's a 485 positive signal and a 485 negative signal. And looking at the chip, it's half duplex, so it can only transmit and receive, like it can't do that at the same time. So it seems like there's only one in signal for transmit so we need one for the 485 positive, so it'll go in and then go out the 2 pins. And it's the same for the 485 minus, so that's why we have 2. We were planning on just figuring out what software was doing with the motors and just talking to you guys more after PDR, just to kind of finalize that design. So.
Is that like right now we're using 1 chip in a half duplex configuration because the chip has the positive and negative lines in 1 chip?
What chip are you guys using? Okay.
Yeah. So we can talk after.
Yeah.
Sure.
Okay, yeah, sounds good.
I believe the motors themselves are only half duplex, so there's no point in going up to full duplex on the heat side if you can't communicate that.
Okay.
Yes.
On the TNT schematic, you have a 5-volt input from the power distribution.
Let's see. Yes.
Why? As far as I'm aware, the TNT itself is powered from the Jetson, and the TNT itself will put out 5-volt lines from the power distribution Jetson.
You can, I believe you can also power the TNT through this pin. And so we can power, we are going to have a 5-volt rail anyways through the power distribution board.
Right, it's more of but we need to go and cut the power lines that are coming from the Jetson. Because we have.
Yes, yes, you're right. It's something, yeah, we'll talk more about this with you guys later.
I just really don't want to have a situation where the power distribution board
It's
fails.
not going
to.
Right, yeah.
Yeah.
So on this year's TNT board, there is a physical switch that goes and turns motors on and off. Is that being considered for this year?
I think so.
It's not going to be considered.
Yeah, no, we're still in talks of that. So this is just a preliminary design that we just like put together. But yeah, like that physical switch that turned. Yeah. So you want that again? Yeah, we could.
Very useful.
Okay.
Yes, Peter.
All my questions are about the P&H box. Step 1, do you have any ideas on the overall dimensions of the box right now?
I didn't have it written down, but I was given specific dimensions that I followed when I created it. And I was also told to make it like about 1/16 of a millimeter thick. That was like for the box thickness, because it didn't have to be that thick. It's like a very sturdy.
Do you mean 1/16 of an inch or 1/16 of a millimeter?
Oh, an inch, my bad, yeah. Yes, it is.
Fantastic. So the box is currently, so you're given specific dimensions. Are those dimensions, do you know if those dimensions are in relation, who gave you those dimensions? Aziel, okay. Do you know if those dimensions are in reference to the size of the frame? Or do you have any idea where these dimensions came from?
I'm pretty sure they're for the size of the frame, yeah.
Okay, great. You've not started to lay out the components within the box yet?
No, but that is very promptly gonna be done though, because all the components that we need are together now. Like we've chosen, like we've made our part selection for that stuff, so now it's just kind of like, yeah.
Fantastic. Are you gonna have the same lid system as last year?
Ideally, yes.
Yeah. Ideally, yes. Great. Do you want the same mounting system to the rest of the robot you had last year?
It worked fine.
Worked fine? Because Haziel has talked to me about trying to have latches.
Yeah,
to make it more easily removable. You want that?
Yeah, he talked to me about the latches too. It seemed like a good idea.
Okay. And so you're the main person working on the box?
The CAD at least, yeah.
The CAD? Okay, great. I'm gonna talk to you later. Fantastic. When do you plan to have the box done such that we set up the printer case?
Honestly, like within like the coming week, like on Tuesday's meeting, I'll probably be able to have like almost all of it done.
Okay.
Is there a way to downsize? So it sounds like you have a little bit less components going on because our motors combine some of the old components that used to be in the P&H box. Is there a way to downsize the P&H box to save mass at all?
Potentially, it wouldn't be a ton of room that we'd be saving just because we did stack the motor controllers on
So
top of each other last year.
But we don't have any this year.
We have one.
We have,
Two, or one saber tooth.
Yes, yeah, because they dual channel.
and we're pretty much using almost the same amount of board, like custom boards as last year as well, so.
How many motor controls were last year?
We had 3.
Okay,
Yeah,
you
6.
stack, did you just stack over on top?
There's like a little pyramid.
Yeah, yeah.
Oh, okay.
Yeah.
Sounds good. So it can't probably be that much longer.
Yeah.
Are these network converters going to live inside the box as well?
Yes, yeah, the power distribution boards in some box.
Oh, yes,
Yeah. Yes. One of you.
Okay.
I don't care.
Is the P&H box going on top of deposition?
Yes, please.
And the battery mount, is that gonna go on the frame, or I brought it up at SDR? Is there a way to incorporate the battery onto the P&H box? I understand why you don't want it to be inside the P&H box, but you somehow find a way so it's right next to it.
Yeah, we could probably find a way to attach it. Well, no, but it could be attached to the box. Yeah.
So I can't leave it?
Yeah, I think
I'm gonna put that up there.
I'd like to. Yeah, I'd like it to be onto the frame. It's chunky.
Okay.
Is the box gonna be on top of that position? That's what you said?
Yeah.
Yeah.
So that's like regular options.
That's what we had last year. And-
I guess.
Sophia.
It's like.
Yeah, the idea to minimize that is the excavation truck, right? Is why we're comfortable.
Yes.
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 So I actually have a question that's not about the box.
Yeah.
So the battery protection circuit, we have a battery protection circuit that we're going to have in the box and then remove for competition.
Correct. Yeah, you can just bypass it.
Okay, so does that mean that during competition runs there is no battery protection?
Correct. The battery protection circuit is only to make sure that the battery does not get discharged too much. So say somebody leaves it on overnight in the BIDC.
Okay.
That is the purpose of that.
It's a different name for it.
Yes. Yes.
Did you use USB ports last year?
Yes. Yeah. We used one. And no. Yeah. There's special USB bulkheads for those.
Yeah.
Yes.
Can you go back to the overall schematic that you had somewhere in the first?
Yeah. Here we go.
Where is the e-stop?
The e-stop is connected to that power distribution board, which has the main relay.
Are we using quick connects this year for that robot? Like just for wires? Like.
The plan is, as far as I know, to continue using the Anderson power pole connectors, which are.
Okay, and they were okay,
Yes.
reliable.
Yeah, those are very reliable. Yeah.
With the USB connections, are you gonna have like a way that you can't secure those, so they can't fall out? One of those little tabs that you screw on it?
That's a good point. I haven't looked too much into the USB bulkheads. Have you?
Yeah, no, I saw playing in the shrouds, but I wasn't really sure about that, but I'll definitely consider that. It's very good.
Yeah. Any other questions? All right, perfect. Thank you.
All right, almost last but not least, second part of systems. So back to our engineering life cycle. This is where we are. As you can see by the lovely arrow there, we are at PDR. CDR is coming up, so we're almost in the fabrication stage, moving forward. Speaking of CDR, it is currently planned to be on January 18th, so that is the first weekend back from break. So not as much time as it seems. Location details will be sent out closer to actual CDR, and by then, sub-teams should have finalized designs, schedules for manufacturing and testing. And next slide right here has some more important deliverables. I'm not gonna necessarily go over all this right now, but there is a checklist in Drive. It's in Drive, you go to review gates and then review trackers. It should be labeled as CDR review tracker. Any questions on those? There should also be templates on a lot of this, either in Notion or in Drive. You may have to look. If you have any questions about templates or what needs to be done for any of those, just come find either me or Grant and we can help. Other upcoming deadlines. STEM engagement report is due on the 15th, team photos on the 16th. Presentation demonstration, which is pretty big, will be on March 10th. Systems engineering papers, April 9th. Proof of life, April 21st. This is also all on the big schedule that is in Drive. If you go find the Google Sheet, it's just in the main folder of the Drive. DFX approval system. So DFX is our design for X. So for example, design for requirements, design for revisions. It basically allows us to have kind of an overall systematic approach to successful manufacturing while making sure we're also meeting those technical objectives that we've been designing. So it's in Google Drive under systems and then under checklists. So there are two things in that folder. There's a DFX checklist planning document. So that's kind of overall just like questions to consider as you're going through DFX. And then you can click on, there's little tabs on one side, little table of contents. You can click on either your subteam or role. So for example, there is one tab for like fabrication. There's one tab for systems. You can click on that, read through the brainstorming questions, read through the checklists. There's also the DFX checklist spreadsheet that will have the actual like checklist that you want to fill out. So that again, you go to the tab on the bottom. It's a little different than it was last year. You just find your tab and that'll bring up all the spreadsheets that you need, all the checklists. So there are 5 categories of checklists. These are divided based on who needs to kind of be concerned about them. So design for requirements, revision, manufacturing, assembly, integration, and repair, and then testing and inspection. Next slide, I believe there is an example. So this is the design for requirements. So this is what it's going to look like in that DFX checklist spreadsheet. You'll see some questions, you'll see a checklist and some notes. So then once you are in that actual spreadsheet, you scroll down and it'll give you each checklist that you need to look over. One last thing for systems, we have been taking notes throughout PDR. So notes for review gauge, or at least my notes, I don't know where Grant's notes are, but I've been taking notes. They're in review gates. It's one document. It just has tabs on the side. So it's the same for all the review gates. If you have any questions there, I may have not gotten all the technical details, but there should be some high level stuff. Okay, close your remarks.
You can say your concluding remarks first.
All right, everyone, we're getting right to the end of our preliminary design review here. All of the systems are looking in a very strong place. The robot is in a very good, very good place. We've got a lot of good feedback, so we're in a great place to move on to CDR. Tasks going forward for mechanical teams include making sure the design is completely, fully, 100% actually done in the CAD. That means all bolts in, that means all fasteners in, that means dust covers, chain, tensioners, sprockets. That means making sure that everything is mounting correctly, that you'll be able to get a wrench on every bolt. For software and power and hardware, that means for power and hardware, that means finalizing wire selections, the power and hardware box, how that's going to mount, component selection, and for software, that means continuing implementation of important pieces and making sure that all of the sensors are mounted and accounted for in mechanical and electrical systems.
And before we all leave today, I just want to say I'm super proud of everyone. This was a really great presentation. I also want to thank everyone that came from outside of Luna, alumni, and also just people that came to give their very helpful advice. And also everyone that watched or is watching, any feedback is greatly appreciated and we take that into account. But yeah, thank you guys for a great PDR. Good stuff.